and DCA matrix. The concept what we are going to discuss here will play an important role when we are discussing the proofs for the Let us consider this case. Suppose we are given an axis of rotation, which is u axis given here. It is an unit vector in that direction. And then we are asked to rotate an arbitrary vector, for example, in this particular case, vector v, by an angle theta about the axis u. The question here is, after rotation, if the vector is v dash, how can we express this vector v dash in terms of the given vector v and the angle of rotation theta and axis of rotation u? Purely algebraic notations in the form of vectors. That is what we are asking. So just to make it clear what we are saying, I will repeat it once again. You are given an axis of rotation u and you are asked to rotate the vector v with respect to this axis u by an angle theta. The new vector v dash needs to be expressed in terms of the vector v, u and theta. Just purely algebraic expression. So this will be useful whenever we are discussing the quaternions as we go along. Let's carry out this exercise. So just to keep this figure in the same location, I will open a copy of this. So you have a copy of this here. Okay, so u is the vector which has to be rotated. Decrease some issue with page. U is the vector which needs to be rotated. Observe that. And then v is the vector before rotation. V dash is the vector after rotation by an angle theta. You can always decompose any given vector into the components of the basis. In this particular case, what we do is we decompose the entire three-dimensional space into the axis u and the plane which is orthogonal to the axis u. So the component of the vector v along the axis u, let us denote it by v parallel, which is denoted here. This is the notation for component of v along the axis u. Let v perp represent the component of v which is perpendicular to the axis u. In the figure, observe that it is along the plane which is represented here. The plane is also spanned by other vectors. We will discuss that as we move along. Then v perp dash is the component of the rotated vector v perp, which is once again perpendicular to axis u. So in order to understand this, you should remember, if we were rotating a vector with respect to, let us say, z-axis, then whenever you have vector along the xy plane, even after rotation about z-axis, these vectors do not come out of the plane. This is an important concept which we had already discussed earlier. That is, if you have a vector orthogonal to the axis of rotation, after rotation, this vector will not come out of this orthogonal plane. So in this particular case, v perp is your component of v along the orthogonal plane to u, and then v perp dash is the same v perp after rotation by an angle theta. Let us consider one more vector w, which is an unit vector in the same orthogonal plane. It is perpendicular to both u as well as v perp. Basically, it completes one more coordinate system there, or along the plane orthogonal, the v perp and w spans the complete system, or they behave like this orthogonal basis for that plane. The problem statement is basically this. We need to express V dash in terms of U, V, and theta. This is what we are going to do. Any questions until now?
No, sir.
Okay, very well. So from the geometry, if you observe the figure, the vector V is a combination of the vector along the U direction and the vector along the orthogonal plane, which is V perp. So V can be expressed as V parallel plus V perp. Now V dash similarly is a linear combination of V parallel plus V perp dash. Observe that if you have a component along the axis of rotation, that component does not change. If you, in order to understand that clearly, we will just open one more copy of this to show you. If you look at this particular example, if you look, this is rotation about x-axis. So if you multiply this matrix by a vector, or if you try to rotate a vector along the x-axis, what would happen? If you have a vector which is already lying in the x-axis, it will have the form a00, where a is a real number. So if you multiply that vector by this matrix representing the rotation, you will observe that you will get back only the same vector along the axis. So therefore, the component of the vector, any vector, the component of any vector, suppose if you had a vector which is decomposed as v1 plus v2, and one of the component is along the axis of rotation and the other components are orthogonal to the axis of rotation, you will notice that the rotation is felt only on the component of the vector which is orthogonal to the axis of rotation. So that is precisely what we are saying here. Oh, what happened? How did I get one more copy? Okay, the system is slow. So V perp therefore is the component of the vector which was in along the axis of rotation, which is V parallel, plus the rotated vector from V perp, which is V perp dash A. In order to compute what is this V parallel, you should observe that when you take the projection of the vector V along the U axis, it is represented as V dot U. In order to remember this clearly, show you one figure. You observe this figure here. So you have this vector R and XY plane. Suppose you wish to compute the projection of R onto the X axis, the component X. How do you determine the component X? It is actually modulus of R multiplied by cosine of the angle phi. Since if you consider the unit vector along the x-axis to be I, it can also be rewritten as the x can be modulus of R multiplied by modulus of I multiplied by cosine of y. This is precisely R dot I. So in fact, if one of the vector, when you take the dot product, if one of the vector is unit vector, the dot product actually represents the projection of the vector onto that unit vector. Projection of the vector under consideration onto the unit vector. Similarly, the y component, what is the y component? Y component is the projection of r vector onto the y-axis, which can be expressed as modulus r dot j, where j is your unit vector in the direction of y-axis. So the dot products are very useful in computing the projection operation. The V parallel, whatever we are considering here, is nothing but component of V along U axis, where U is your unit vector. Therefore, V dot U represents that projection component. The amount, that is the quantity of V present in the U. So, V parallel is nothing but the scalar number V dot U in the direction of u. So that is why this expression is, that is how this expression is obtained. Therefore, V perp would be just a subtraction of these things. V perp is nothing but V minus V parallel from the first expression.
So for this unit
And
to
V
be
parallel is already.
so
Pardon me?
for this units to be a unit vector, right?
Yes, yes. U is an unit vector. That was our assumption. If you go back here, U is the unit vector along the axis of rotation.
Okay. Sir.
You are right. Very good. Thank you for pointing that out. So in order to express this, you should be very careful. This is not possible for any arbitrary two vectors. One of the vectors should be unit vector. Only then the projection quantity can be obtained. So V perp is therefore expressed as V minus V dot U in the direction of U. Sorry. So after rotation by an angle theta with respect to the U axis, the V parallel component remains the same. However, the V perp rotates to the new location V perp dash. Our intention is to compute this. What is this V perp? We have to compute that. So the magnitude of V perp is same as V perp dash. We had already indicated that rotation operation does not change the magnitude of the vectors. So the magnitude is same. Magnitude of V perp is equal to magnitude of V perp dash. So let us resolve this V perp along the V perp and W. Since the angle is known, you can do this. So you have to take a unit vector in the direction of V perp. W is already the unit vector. So since the angle is known, it is just cos theta and sin theta. So that is why we have this expression. V perp dash is nothing but the modulus of V perp or V perp dash, both are same. Therefore, it is replaced by V perp itself. Cosine of the angle theta in the direction V perp divided by modulus of V perp, because that is the unit vector direction. We are taking the unit vector in the direction of V perp. That is why we have divided it by V perp, modulus of V perp. Similarly, along the W direction, it is simply the modulus of V perp or V perp dash, both are same, sine of theta in the direction of W. Is this clear? This is an important observation. Okay, so this we will revisit when you observe the quaternions.
Sir,
Yes.
sir, W is a unit vector in the along the direction of cross product of U and V perp, right, sir?
Very good. Right. So actually, it is. We just mentioned it as orthogonal. Yes, it is a cross product of U and V. Here we have just said W is perpendicular to the plane containing U and V, which is nothing but cross product of that. You are right. Very good. So that is what we are going to replace it with now. W will be replaced by U cross V divided by U cross V perp divided by modulus of V perp. Very good. Excellent. So you replace it in the above expression. You can so remove this V perp modulus gets cancelled out, and then you get V perp dash is cos theta V perp plus sin theta U cross V perp. So U cross V perp is nothing but your W. We will see that it can also be expressed as U cross V. Both are same. Because V perp is expressed as V minus V parallel. So let us look at it. V perp is nothing but V minus V parallel. Therefore, U cross V perp would be U cross V minus V parallel. But U cross U parallel is what?
Zero.
By linearity, you can expand
Zero.
it inside. Yes, it is 0. So therefore, this cross product is simply U cross V perp is nothing but U cross V itself. So at least one expression is reduced. So comparing these two, recall that this is what we had derived until now. We are now going to replace it with this V perp is V minus V parallel. And then we had also stated that U cross V perp was U cross V itself. So this is the expression we have now. The complete rotated vector is you have to add the V parallel component to this. That's all. So V parallel is already V dot U in the U direction. This was our first derivation. So this is what we get. And then you simply have to add V parallel to this. Okay, so V parallel plus V perp dash, you simply add. So this is your expression. On simplification, you obtain this. So you should verify that one of your exercises, if you remember, was to compute the DCM matrix given the axis and angle of rotation. Check if you can use this expression to do that. Okay, that is a hint for you. I will be enabling the assignments soon. Any questions until now? This is just a quick run through your vector algebra, what you had probably been doing it in your 11th and 12th. So all these things are related. We are doing some rotation operations. You have to see how one can be obtained from something else. So to summarize, we have this. This is the expression we had given as exercise approximately. So if you have the direction U is expressed in L times in the DCM notation, be a unit vector along the axis of rotation. And if you have theta to be the angle of rotation, and if small ijk is the rotated frame, you can verify that the coordinate transformation matrix is given by this expression. You have to, of course, verify it. You have to just compute these expressions and then make sure that this is the expression you obtain. Okay, check it out. So let us summarize our entire discussions, what we had now. This is Euler's result basically. It has two ways of looking at this result. Either you can look at the result in a geometric fashion or in an algebraic, linear algebraic or algebraic fashion. Geometric fashion or the rigid body fashion says that if you have a rigid body and then you are looking at the movement of this rigid body. But however, when this rigid body moves, if you observe that one point in the rigid body is fixed, then the entire motion of this rigid body can be described by rotation about an axis passing through this fixed point. So this is one of the results of Euler. Basically, what is being said is this thing linear algebraically. If you have a rigid body, if you fix a coordinate system to that, and then at the origin of the if you move the rigid body such that the origin does not move. If you move the coordinate system such that the origin of the rigid body does not move, or origin of the coordinate system does not move, then if you look at the new coordinate system and the old coordinate system, they are related by this rotation operation. What does it mean? The new coordinate system can be obtained by performing rotation of the old coordinate system with respect to an axis passing through this coordinate system. This is clear. The reason is if you have two coordinate system with common origin, you can construct this DCM matrix, which will become your transformation matrix or rotation matrix. And then you can compute the axis corresponding to eigenvalue 1 or the eigenvector corresponding to eigenvalue 1, which will represent your rotation axis. So this is what is playing a role. Whenever a rigid body is moving such that one of the points is fixed, instantaneously you can associate axis of rotation with respect to the rigid rotation movement. So another important concept to understand is product of two rotation matrix is again a rotation matrix. We have already seen that because rotation matrices are orthogonal, product of orthogonal matrices are also orthogonal. In addition, you can verify that the determinant is also. In fact, composition of rotation is going to give you the complete rotation. And then if you have a rotation matrix which is not identity or which does not rotate by 0 angle, then it has one eigenvalue which is equal to 1. This also we had proved. The eigenvector corresponding to eigenvalue 1 is called as the axis of rotation. So this is the summary. Next we will be going to quaternions. Before that, if you have questions, let me know.
No, sir.
Okay, even at later point of time, you can come back. Let us move to quaternions. Yeah, so quaternions are basically some kinds of numbers, okay, just like complex numbers. In fact, it is a generalization of the complex numbers to a higher dimension. We know this complex number. Let us see what is this relation between complex number and geometry. Complex number has one-to-one representation with your two-dimensional plane. Complex number has one-to-one representation with two-dimensional plane. So we have to see if these complex numbers can also represent rotation, because we are interested in rotation operation. Let us consider this multiplication of addition of vectors is not rotation, which we can easily verify. Let us check what happens when multiplication. So when you multiply two complex numbers, the overall magnitude of the product will be nothing but the individual products of the magnitude. The angle is nothing but sum of the angles. This can easily be verified by this expression. So if you have Z1 as complex number R1 e power I alpha and Z2 as complex number R2 e power I beta, if you multiply these two complex number, what will you get? You will get R1 multiplied by R2 e power I plus alpha. So what has happened? So the vector Z1 has been rotated by an angle beta. Not only that, but its magnitude also has changed or scaled by the magnitude R2 or vice versa. You can assume Z2 being rotated by Z1 and amplified by modulus R1. Therefore, suppose if you fix the magnitude of Z2 as 1. Yeah, so there was some question. What was that?
Sir, you said that addition will not rotate the vector, but if we add with a different angle, then it will rotate the vector. Right? It will rotate the complex number to some angle, some other angle.
Okay, when I said not rotate, okay, so I got your point. Actually, when I said rotate, it won't be systematic in the sense if I use, suppose let us say I want to rotate vector 1 by an angle, some angle, some vector by some fixed angle. Suppose if you used the addition operation and let us say that the rotation vector is R vector or something. So if you add your given vector to R and some other given vector to R, it will not have the same effect. So in that sense, I meant not rotate. Okay. So I got your point. In general, when you add two things, it will always rotate and scale. That will always happen. You are right. But it is not consistent in the sense the operator, if you fix. So every time you add new vector, you will not get the same effect.
Okay, sir.
So here, let us see what happens in the Z2 case. If you fix the modulus of Z2 as 1, that is R2 is equal to 1. Then if you multiply Z1 with Z2, what will you see? The modulus of the product is same as modulus of R1 or Z1. And then there is an additional rotation happening by an angle beta. So in fact, you can multiply this with any vector. The effect will be simply rotation by angle beta. That means you can always fix one of the complex numbers and then you bring in new complex numbers to get the rotation effect. So this is what I meant by consistency of the operation. But your statement is also right. So we cannot simply say that it does not rotate. We should say that it does not have a consistent effect. Okay, is that clear now?
Yes, sir.
Thank you for pointing it out. Yeah, very good. So how to rotate vector in 2D by angle theta is basically, this is what we have discussed. Express the vector as a complex number. To rotate a vector in the two-dimensional plane by an angle theta, you just need to multiply this number, which is representing the vector, by another complex number by having norm 1 and angle theta. Basically, multiplication behaves like a rotation operation. Is that clear? So if this is clear, we have to ask, or we would like to ask a question. In the three-dimensional space, can we do this? Can I multiply two three-dimensional numbers in some special way? Understand that complex number multiplication is a special multiplication. If you are given a vector in 2D expressing x1 and y1 and another vector x2, y2, I could have simply multiplied these two by x1, x2 and y1, y2, or x1, y1, y1, x2, y2. I could have done so many other possible ways of multiplication. But this complex number multiplication was specially designed such that a two-dimensional number is behaving almost like a real number. In real numbers, you can do multiplication, addition, and then there is this distributive property. There is this inverse in the multiplication, inverse in the addition operation. So all these things, whatever the real numbers can do with plus and minus, the plus operation and the multiplication operation, the complex numbers can also do. That is your two tuple, or you should say just a pair. The pair of numbers, which is representing a vector in the R2. So you are able to multiply the vectors in the plane by this special definition of multiplication, which is your complex number. So when you do with such a thing, you obtain this rotation operation. We ask the same question, is it possible in the three-dimensional case? I will give you two triplets. Can you multiply it in a special way such that it consistently behaves like rotation operation? This is actually a very profound question. This was this is what we are asking. Can we multiply two three-dimensional numbers in a special way? It should have this, it should behave like your real number or complex number. What kind of complex numbers should we use for such rotation? The answer is hypercomplex numbers, which was invented by Hamilton in 1843, approximately. Here, what he found out was it is impossible to do with triplets. That means you can never define a sequence of multiplication operation which can consistently behave like your complex number. This was what Hamilton found. In fact, what he found out was he required set of four numbers to define this multiplication operation in the hypercomplex domain. That means you don't have one complex number now, you have multiple complex number. So in the quadruples, you have a scalar and then three sets of complex numbers, I, j, and k. I think somewhere in your 10th or 11th or 12th, this would have been defined, right? So I square, j square, k square is equal to ijk equal to -1. If you can make such a definition, then if you represent any number as a linear combination of these three plus a constant 1, then it is possible to define the notion of rotation. We will see how as we go along. So quaternions, or this is also some kind of really complex numbers. It's of rank 4. Your standard complex numbers is rank 2 because it has only 2 degrees of freedom. They are not filled, but non-commutative division ring. We will answer. Don't worry about this name. Field basically means the behavior. Is it similar to real numbers? In real numbers, you have two operations. each of what are those two operations? The plus and the multiplication operation. They are the main operations. The plus operation and the multiplication operations are commutative with respect to themselves. They are commutative group. Multiplicative operation, if you remove the zero identity of the additive identity. What is additive identity? If you add any number to that, you will get back the same number. That is your zero. If you remove the zero, the remaining set of numbers is a commutative group with respect to multiplication operation. You have inverses also. You have additive inverse, you have multiplicative inverse for everything except zero. And then the plus and the multiplication distribute one of them. What is that? Multiplication distributes over the addition operation. The complex numbers also has a similar behavior. You can see that addition and multiplication are commutative. However, when we go back and define these quaternions the way we have done above, that is I square, j square, k square is -1. You have three sets of complex numbers which are sitting in the, which are almost like sitting in the orthogonal domain or something. And then they interact with each other in a way that is I, j, k equals to -1. This set of numbers is not commutative with respect to the multiplication operation. That we will see it immediately when we start working on more details. So it is non-commutative, but it is a division ring. What do you mean by a division ring? Division ring means every number will have the inverse. So even though it is non-commutative, every quaternion has an inverse. That is what it means. Non-commutative basically means it does not have, it is not multiplicatively commutative. The multiplication is not a commutative operation. Division ring basically means there exists inverse for, multiplicative inverse for every non-zero quaternion. Basically, it satisfies every property of the field. Field basically means what I explained for real numbers and complex numbers, where you have the plus operation and the multiplication operation and the interactions between them. They have everything except commutative. But this is okay for us. We will see as we go along. So any questions until now? Don't worry if these last two statements are this. Okay. And what is important is to understand this. And if you want to prove this statement, you may have to probably write thesis and thesis on this. It takes a huge amount of algebra, understanding this algebra to prove these kinds of statements. You may have to do an MSc degree completely even to get anywhere near that. In mathematics, that too. That will be probably some 10 or 12 courses you have to learn. Okay. So this is what the quaternions are. It is a four-dimensional space. It is associative. Associative basically means associative law holds. Normed. So every number has a norm. So your complex numbers are normed. So you can compute the norm of a complex number. It is a division. So every non-zero quaternion has an inverse. Algebra. Basically, you can multiply these numbers over, multiply and add. So that is why it's called algebra. Over real number. So don't worry about these complex names. We will be defining the expressions. Algebra basically means it's a vector space with product operation. Complex numbers are vector space. It also has a product operation, and then it is not some any normal product operation. The product operation are also nicely behaved. You can multiply complex numbers in nice way to obtain nice results. Whatever that niceness means. Niceness basically means that it has the inverse and things like that. So division algebra basically is division is possible. If you say that A equals to Bx and A and B are not 0, then the expression X is unique. That is what division algebra means. That means you can compute the inverse of B, left inverse probably here. Associative division algebra means multiplicative inverse exists. You should remember that associative law is an extremely important law which we actually take it for granted because that is the one which has given rise to existence of inverses. existence of inverses for non-zero elements. So the notation for complex number is C with a box or something, and for quaternions it is H because Hamilton discovered it, but we sometimes, yeah, because of Hamilton. So C is a finite, important statement we are going to make now. C is a finite dimensional division ring containing R. What does it mean? C is finite dimensional over R. That means what is the dimension of C as a vector space over R?
2.
It is 2. Okay, so if you basically 2 linearly independent vectors are required to complete the vector space C. It is a division ring which we have seen. You can multiply the numbers. And then the division inverse exists. That is what indirectly means. We have shown that when A equals to Bx and A and B not 0, then X is 0. That is what division ring means. And it contains R. So one of the axes is R.
Sir,
Yeah.
sir, C should be in field, right?
See, it's also a field. Division ring is also a field. No? Division ring is a generalization of the ring and field. What is the difference? Ring may not have inverses for every element. Field means inverse will exist.
Division ring and field are same.
Hmm?
Division ring and field are same then.
Yeah, kind of. You can say finite dimensional field containing R.
Okay, sir. Sir, but you said that the commutative property doesn't hold inside division ring or something.
Yeah, for this one, for quaternions, it does not hold. Division, see, ring is a generalization of the field. So if in a field, usually field is defined for commutative things. In a field, the multiplication is a commutative operation. I have to go back and check, okay? And then in a ring is a generalization of that. Anything is a ring. There may be some elements with, for instance, set of polynomials is a ring. You can multiply the polynomials, right? But you cannot find out the inverse. So inverse 1 divided by a polynomial is not a polynomial again. It is not closed under that operation. So polynomials are ring. In that sense, I said ring here. It's a
Okay, sir.
generalization of that statement. So field and ring, so field is a subset of ring. So I can say it is a ring, C.
Okay, sir.
So real numbers contains integers. In that sense, rings contains fields.
Yes, sir. Yes, sir. Got it.
Yeah, very good. Thank you. The important thing is this statement. The set of quaternion is the only other finite dimensional division ring containing R. Okay, you cannot find anything else which has this multiplicative or the finite dimensional division ring property which can contain R. This is an important property. These are the ones which takes huge. It's not easy to prove all these statements. So I also do not know the proof, but I only understand the statement that the set of quaternion is the only other. In fact, what does it mean? It means you cannot construct any other complex number other than this Hamiltonian, which will have these nice properties. Okay, you cannot construct three-dimensional ones. We did not prove it, we mentioned it. So complex numbers and this set of quaternions are very special. These are the only two finite dimensional division rings which contains the real line. Okay, so these are only for your interests. Our aim is only to manipulate these numbers. Okay. If you have any questions until now, please ask. But yeah, all these things are just to motivate and then give you some directions. But what we will be doing is simply manipulating these quaternions and then extracting out these rotation properties.
No, sir. No question.
Okay. So let us look at this quaternions in more detail now. In from an operator's perspective, basically will be how to operate this. Let us see. They are formed by a three-dimensional vector part and one scalar part. The components I, j, k will represent the three-dimensional vector part. I can be thought of as 100, j is 010, k is 001. These are just representations, okay? And in general, q is a 4 tuple. That is, your quaternion is given by 4 sets of numbers, q0, q1, q2, q3. In our, all these numbers are real numbers. Or, so usually, we in our course, we will use q0 as the scalar part. Some people use q3 as scalar part. You should be careful to look at the definition. So in our course, we will be using this q0 as the scalar part. The remaining thing, we will call it as the vector part of q. So this is how, in general, just like complex numbers, if you remove q2 and q3, it is like usual complex number. So any quaternion is a linear combination of q equals to q0 plus iq1 plus jq2 plus kq3. Remember this, this is one way to extend the set of ideas of numbers. If you are given set of only rational numbers and then you are asked to add or include one irrational number square root of 2. So how does the complete set behave now? How will you represent this complete set? If you are given set of complex numbers, sorry, set of rational numbers, and then you are asked to add one irrational number into that set. I think these are some of the problems you would have studied in your 11th and 12th. If you remember, let me write it once. Just a minute. I'm just trying to see it's not moving. Yeah. Okay. Suppose you are given a set of rational numbers. How does rational number look like? P divided by Q. Q not equals to 0. And P and Q are in integers, set of integers. Yes, this is your set of rational numbers. Suppose you are given square root of 2. And then can you construct the complete set which contains q and the square root of 2 with the appropriate multiplication and addition operation? So suppose if q belongs to this one or q1, q2, so your q integrated with 2, this is one symbol for you, is expressed as q1 plus q2 times square root of 2. Have you come across this expression? It represents the set of all rational numbers, and then you have included the square root of 2, one irrational number, and then you have defined the operations also. So in fact, this set will have all your properties, inverse and everything you can compute. All of them will lie in the same set. So these are some of the exercises which would have been given to you when you had doing your 11th and 12th. So this is called extension. Okay, so this is also called field extension, field or ring extension. So if you remember, you had set of real numbers. And then you looked at something called x square plus 1, a polynomial in R. So if you look at the roots of this, so where does the root belong?
Complex plane.
Yeah, it's actually no roots in the this domain at all. Okay, no roots in R. So what did you do? You simply hypothetically invented let I be the root. Okay, whatever it is, you don't know. Here it is let square root of 2 be the expression. There will be, can you tell me, does anyone know what is the sequence which converges to square root of 2? Sequence in Q converging to square root of 2. So square root of 2 is approximately, in your mind, you know that, no? 1.1412 something something. You can always look up this expression saying that the sequence which converges to this will be sequence or series, whatever that is. I would say, I can start from 1, then I will say 11 by 10, then 114 divided by 100. Like this, we can go on giving you this expression. So this one belongs to the Q, but this converges to some place, and that something is actually represented by this symbol. It is only a symbol, okay? You don't know what it is. And then how did you include it in your complete Q? You simply said Q included with this convergent sequence is your new domain. Q1 plus Q2 square root of 2. This is just a symbol. In the same way, what we did here is you introduced some new symbol. So I is a symbol which has property. What is its property? I square equals to minus 1. If I is a symbol which is having this property, what you did was you took the set of real numbers and included this I also. So how will it behave? It will have real number 1 and I times real number 2. So this is nothing but your complex domain. This is what we have done. So in the quaternion, what we have done? You have taken real number and then you included I, J, K. So here you can imagine I could have included in the rational numbers square root of 2, square root of 3, and whatever irrational number you want, you include it here. If all the irrational numbers are included, it finally becomes R, your real line. So here this one has become your quaternion H. Does that make sense?
Yes, sir.
This is nothing but Q1 plus Q2 I plus Q3 J plus Q4
H,
K.
K.
But they have some special property. You have to define these special properties also. A square, J square, K square. You have to define how they interact. I, J, K. This is an important thing. Equals to minus. Here the square root of 2 and square root of 3, how do they interact? Square root of 6. You can take inside and multiply. Not only square roots, you have to take cube root, fourth root, 100th root. So many things are there. These are just expressions. So every irrational number, if you include, it will become R. So here we had introduced some symbols I, J, K, which had this special property, and their interactions also have to be defined. So I square becomes a real number. Here, so square root of 2 whole square becomes the rational number. So those are your defining expressions.
Sir,
Yeah.
Sir, this Q, when you included root 2 inside Q, it became like Q1 plus Q2 into root 2. If you include like root 2 and root 3, then this will not hold, right? It will need some four terms.
Yeah, it will require more. Now what you have to do is Q1, very good. Q2 root 2, Q3 root 2.
Root 3.
You should keep on doing that actually.
Okay, sir, like
including more and more. And then define operations between them also. How do they interact? All those things you have to define.
okay, sir, like it should, we can define by 5 terms only, right?
Pardon me?
like only root 2 and root 3 are there, then we can define with 5 terms, like Q4 root 6 and Q5 root 2 by 3, something like that.
No, root 6, do you require, okay, that's a good question. Do you require more or this only 3 is enough? Sorry, let me delete it. How do you remove? 1 minute. So if you had root 2 and root 3, in my opinion, you just require Q1 plus Q2 root 2 plus Q3 root 3. You say that you also need the multiplication of these two also, is it?
Yes, sir. Q4 root 6,
Plus Q4 root 6.
then division also, sir. Root 3 by 2 and root 2 by 3.
Are you sure?
Like I didn't study this in my 12th. I am just telling like out of
Just
reasoning.
check it out. That's interesting. How many terms to include such that the set becomes closed? Okay, that's a good point. Okay, I have not thought right now. We have to work it out. Only then we will know. That is, Q will contain square root of 3, square root of 3. How many terms? How many minimal number of terms? Okay. Yeah, but good question. Okay, that's a good way to ask. How many terms? What is the minimal number of terms that is to be included? I'm just questioning this. I'm not making any statement. No? Do we need to add more, or whatever was there is enough? We have to basically you have to basically do those operations and see whether it is going out of the domain. When it goes out of the domain, you include those component also. So that is what we have been doing here. Even the complex numbers, when we had the square root of -1 was not there, you simply included in the domain. But fortunately, what happened was once you included that I, any polynomial with complex coefficients also has roots in the complex domain itself. You don't have to go beyond complex numbers. So therefore, complex numbers are also called closed under algebraic operations. Closed under algebraic operations. Algebraic operations means basically these polynomials and other things. That is an interesting property for complex numbers. Okay, so no other thing. You cannot do that in a finite field later on. If some of you are interested in cryptography or something, one can talk about something called finite fields. So if you look at what is the minimal, if you look at this F2, if you take these two numbers, you can define addition, multiplication. It has all properties of fields. This is your binary numbers, in fact. So binary numbers is a field. Whatever you are using in computer, actually it is that is the high and low. It has this mathematical field property because of which it has many applications in cryptography and other things. So some of the questions that are asked is, so I can define some polynomials in F2. So some of the polynomials will not have root in the same domain. So one can ask such questions once again that I can add more quantities into the F2 to make it just like complex numbers. We can expand that. So you can go on expanding. There will be no place to stop. In fact, the complex numbers, what we found out was, if I added an element into the, that is I was added into the real number. So any other polynomial in the complex domain has roots in the complex domain. But for the finite fields, you will not find such a good property. So complex numbers are nice numbers, that is why. So finite fields are not closed under this algebraic operation at all. So you can have infinite number of extensions, like whatever we did. All properties of field. so that you won't get confused. Okay, so we will not go into that. It's a digression, but just to see the linkages with other areas. Okay, so let us come back to quaternion. Quaternions are set of 4 tuples. Q0 plus IQ1 plus JQ2 plus KQ2. IJK behave in a special way. I square, J square, K square are -1 and IJK is also -1. Many times we write it like this, that is Q0 plus vector part of Q, where vector part of Q is IQ1, JQ2, KQ2. Okay, so once we have these things, let us define 1 or 2 operations before we leave for the day. So how do you add 2 complex number? How do you define equality of a 2 complex number?
If the magnitude is equal and angle is
Equal
like
as a
2
very
pi.
good. That is one way, or the other way is you simply look at the components, right? If the components are equal, then the complex numbers are same. Can we make that statement? So
Yes, sir.
2
Yes, sir.
quaternions are equal if the components are equal. The most trivial definition. Okay. So this is equivalent to complex number. And how do you add 2 complex number? Component wise addition. Same thing. So in the quaternion also, you simply add 2 quaternions by adding them component wise. But the sum is also fortunately quaternion. So it is closed under something you have to remember. Whenever you do some operation, it should be closed under that operation. And then how do you take inverse of the quaternion or inverse of the complex number? If you take negation of all the numbers which are given, then it will become additive inverse, even in the complex number as well as the quaternions. It is very important to observe that it is both commutative and associative because we are doing only component wise operation. So addition, we have no problems at all, fortunately. For quaternions as well as complex number. Let us look at the multiplication. In order to use the define this multiplication operation, we have to use this property I square, J square, K square, and I into J into K. So when you use this, all these things equal to -1, you observe that Ij is equal to K. Can you prove the first quantity? One of you, I multiplied by J.
So we can multiply ij k by k.
Correct. On the right hand side.
Yes.
If you multiply on the right hand side by K, you will get -Ij equals to -K.
Excuse me, sir.
Similarly, you have to somehow prove this J as well. Yes.
Sir, can we continue next class, sir?
Yes. This is the last part, the simplest part I am going. I will be stopping now shortly.
Sir,
Yeah.
sir, to multiply like IJK with, sir, I know my voice is echoing, sir. Hello, sir.
Yeah, I can hear you.
Yes, sir. To multiply IJK with K, that K square, if we are multiplying separately, then we need the associativity rule before that. Associativity of addition. Sorry, multiplication.
Yeah, associativity of
Multiplication, sir. Like,
yeah, you can put the braces anywhere. That is why that in the IJK braces were not put at all. So that associative property is also there. You are right.
sir, so we assume that this is associative before.
Yeah, associative law we are assuming. We are
Okay, sir.
yes.
Okay, and sir, minus we are bringing to the front, so we are also assuming it is commutative.
No, commutative we are not doing, no.
So -1 was at the end, right? K square is minus, which is at the end. So we are bringing it to the front.
Oh, you are okay. So there is a mixture of operations now. So you are saying that minus is a real number. No, commutativity we are not assuming. That is, you can imagine that to be -1. Minus the real numbers commute with the complex numbers. That is the assumption we are making here. Yeah, good point.
Okay, sir.
The real number -1 is commuting with the number. Just like in the matrix you write, no, you can write not the matrix. Okay, so I don't
Scalar
have
multiplication.
analogy for that.
Scalar multiplication.
Scalar multiplication, we do that. Yes, on the right hand side or left hand side. Right.
Okay,
So
sir.
that is all. That is a different operation. Correct. How do we represent it rigorously? I don't know. Yeah, that is also an assumption. Associativity, I'm not sure. Are we assuming associativity? When you don't express the braces, it means it is associative. IJK, when we write, the symbols are associative. The overall multiplication also then automatically becomes associative, you are saying, by that assumption.
Yes, sir.
Yeah, it happens to be true also. So go back and check whether these other properties are holding. So I will stop here because this is an important location where we are there. Use this I square equals to j square equals to k square equals to ijk equals to -1, and then derive the rules which are listed here. Okay, I will stop here. Any questions we can discuss? Otherwise, the class is over.
Sir, can you update the PPT on the model?
Yes, yes, I will do it shortly. Immediately, I will do it.
Okay, sir.
If I don't do, please remind me in my email also.
Yes, sir.
Okay, thank you. Okay. So, okay, so I will stop sharing. If you have questions, comments, don't hesitate.